Okay, let's get started here. So are there any questions before we begin? I just want to briefly talk about test number 1 since we are going to have it in 1 week. So since our last class period, I put together what I call formulas and functions document. It's available on the graded webpage of the course website. And basically you can use this during the tests so that it can help you with various formulas, mathematical expressions that we've talked about in our class so far. And eventually, as I page down, you can see what I've tried to do is get all the main functions that we've talked about in our class. So this could be a quick reference guide if needed during the tests. So during the tests, you're welcome to use this as needed. Now, again, as I said before, this is a closed book, closed note test, but you will have access to my R programs and data files. So obviously, if you haven't been doing this already, it's good to get familiar with my programs that are available on my website. They will all remain there during the test. All my notes will be gone. You want to have access to those. Now again, you're going to be using the computers in the classroom here, and so on Tuesday after our class, I wanted to take a closer look at these computers. So I logged on, and unfortunately it looks like they have an old version of R on them, version 4.0.5. I think now we're up to, about version 4.2, if I remember right. Yeah. And what can happen is when you have an older version of R, sometimes some packages may not install properly. And so, the main packages that we've talked about so far where you would need to actually download them are RGL and MVT norm. MVT norm worked fine, RGL did not. So because of that, I will not have any questions where you would need to actually implement anything from RGL. Now I still might, let's say, put results on, I might put something on the test where maybe I've ran some code, let's say using RGL, and you need to interpret it in terms of like the corresponding output and stuff. So don't think that a three-dimensional plot of the surface of a bivariate normal wouldn't be on the test. It could be on the test. Let's see here. Now there will be no paper distributed with the tests, meaning that I will essentially allow you to download the test electronically from my course website, the graded web page, and it's going to be in a Word document, and you'll be able to type all your answers into that Word document. Note that I do expect for your answers to show me not necessarily, let's say, the numerical answer, but also to show me any formulas you use, any kind of R code you use for the test. So you always have to show your work. So very simply, let's say if I asked you to calculate an estimated covariance matrix, like what we did towards the end of last class. If you just put the estimated covariance matrix there, rather than show me how you got it, you will not receive full credit. The reason why I require that is because it's actually beneficial to you. Because let's say if you made an error in your calculation, and you got the wrong number, and you only gave me the number, well, I don't have any way of really determining, well, maybe it was just a very small error. And so by you showing me the work that went into the actual numerical calculation, then I can give you partial credit on the test. So that's why, again, you always need to show your work. That can be done by showing like what kind of formula you're using. It can be done through showing me all your R code and output. Okay, any questions about that? Yes.
I have two questions. So we don't have to do it by hand. We have to do it with R, yeah?
Yes.
Okay.
I strongly recommend it.
Yeah, so, and the second is that you said we have access to your programs in your website. You mean the R things, the R codes by the program, or what? We have access
All
to
these
all
R
of
programs.
Oh, just the R's.
Just the R programs. I will actually remove access to any of the
Oh, okay.
notes beforehand. Okay?
And then we have time for whole decision, like 1
Excuse me?
hour? And the time would be like 1 hour?
We'll start at 8 a.m. and we'll go up until the end of our class period. And so when you're done with the test, then just simply email it to me. But don't leave the classroom until you receive a confirmation from me that I've actually received it. Okay?
You wouldn't be here?
No, I will be here.
Okay.
But I've given electronic tests like this for quite a few years, and it's what I have found is just good practice to verify that indeed I have actually received the test. So I don't want you to leave and I say, well, I never received it. Well, in the meantime, not saying that any students in our class would do this. In the meantime, maybe the student didn't actually email it to me, went back to their office and decided to keep on working on the test and said, oh, but I did email it to you. Maybe somehow it got lost in the email. So I'll talk more about the test next time. We will do a review for the test. Maybe probably look at maybe some old test problems that I've given corresponding to this material as well. So since we will have a review, that's also obviously a good time to bring any questions that you may have on the material. And again, the purpose of this first few weeks of the course is to get you up to speed for the real multivariate part of the course. This material that we're talking about, most of it, some of the stuff with the multivariate normal, I completely understand that probably a lot of you have never seen it before. But the other stuff, like the matrix algebra, the intro to R, some of the introductory stuff for the data distribution and correlation section, ideally, I would like all students to come with that background already. But what I've found is that that's usually not the case. And all of you are coming from, or many of you are coming from quite a few different majors, and so you're going to have different experiences. And so I found it works best to do this this intro part first. Okay, so today we're going to talk about, or we'll probably finish the data distributions and correlations section. What we were talking about last time was simply how can you estimate a mean vector? How can you estimate a covariance matrix? How can you estimate a correlation matrix? It's not really too difficult. But now we're going to relate this to this bivariate, meaning we have two random variables in our vector, this bivariate normal distribution that we've been talking about. So here's the actual normal distribution again. And, oops, there we go. And what I would like to be able to do, well, first of all, so what this normal distribution is basically representing is how items in our population are distributed. I would typically expect items on average to have a mean of 15 for x1, a mean of 20 for x2, and that covariance matrix gives me information about how much variability I would expect amongst these x1 and x2 values that I actually observe, and how much dependence there is between them as well. And so let's take a look at a sample from a population that's characterized by this probability distribution. And so this is going to be, again, very similar to what most of you would see in a Stat 801 like class, where let's say a univariate normal distribution is defined, and then the instructor says, okay, let's simulate a sample from a population characterized by that probability distribution. So we're going to look at how we can simulate from a multivariate normal distribution here. So the first thing that I need to do is get the mean vector, get the covariance matrix into R. We've seen this before. And I'm going to take, and in the end, I'm going to take a sample size 20. So I'm going to create an object called N. That's my sample size. Now to simulate the data, if you've done this in R for a normal distribution that functions R norm, for univariate normal distribution. Now, since we have a multivariate normal distribution, we have to use a function from MVT norm, that package, to do this. And the function is R for random, MV for multivariate, and norm for normal. And simply it works where the first argument is a little n. Well, you put in what your sample size is. Then you put in your mean vector for the mean argument and the covariance matrix for the sigma argument. And so if I go ahead and run this, this is what I get. So my very first sampled item is a vector that is 17.03 for the observed value of x1 and 19.51 as the observed value for x2. My next observed value of x, you could call this the x2 vector, will be 15.6 and 17.7. The x3 vector, 16.1, 20.99, or 98. Okay. Now, what if I ran that exact same code again? Notice I got something different. Again, I'm taking a sample, a random sample essentially from a population characterized by this population. And then if I run it again, I get another sample. Why am I getting different samples, even though I'm running the same code? What?
It's a sample. It's a random sample.
Yeah, it's a random sample. Okay? And we're simulating what the sample would look like. Now, especially for teaching contexts and also for research contexts, it would be nice if we could somehow always get the exact same sample. And the way to do that, whenever you're simulating data in a random manner like this, is what's called set a seed number. And so in R, there's a function called set.seed, and in parentheses, I can just put any number that I want. And what this number inside there, or how this number inside there is used, is basically the internal algorithm that RMV norm uses, takes into account this seed number that you're setting in order to, let's say, grow the sample a certain way. And any time that I run this code with exactly that same seed number, I will get exactly the same results. Now, if you don't set a seed number, basically what R does is basically use the time of the day as a way to come up with a seed number. It's not really too important to get into the details of seed numbers and random number generation. Just the fact that we know how to simulate a sample, and we can always get the same sample by setting a seed number is what you need to know. Okay, so we can then use some methods that we've done before to estimate then the mean vector. We could use the call means function, which stands for column means. Find the means of each column of x, and put that into mu.hat. I can use the co function to find the estimated covariance matrix, and the core function to find the estimated correlation matrix, and this is what we get. Now remember, for our normal distribution itself, it had a mean, our mu of 15 and 20. Look what we get for mu hat, the estimated mean vector, 15.29 and 20.03. Kind of close. Well, you would hope that that would happen because it's coming from a population that we know what it looks like. We would hope that the simulated data would kind of match up. The covariance matrix, remember the variance of x was 1. Here's the estimated variance, 0.93. The variance of x2 was 1.13. We had originally set sigma 2, the variance of x2, to be 1.25. The covariance is estimated covariance is 0.55. We had set it to be 0.5. So we're getting what we would expect. That's good. If we didn't, we'd be very worried about if this function is actually working. Now, so in the end, these estimates are reasonable given our population. What would you expect to happen to these estimates if I were to increase my sample size? Anybody know? What would you expect?
Closer.
Yeah, thank you. They're going to get closer. And in fact, you can do that on your own. Again, think of my code as a, well, I guess we'll do it here real quick. Suppose I took a sample of 2,000 instead. Oh, okay, well, we just have to be patient. I have it set up so that I can actually see everything being printed, and that's not the default, but sometimes it's useful to see that. And we can see, look at that mu hat vector. Indeed, it is quite closer to that mu. In statistics, there's a special name for this property that as, let's say, the sample size gets bigger, what's going to happen to the estimates in terms of they do get closer to the parameter values. That statistical property is referred to as consistency. Maybe you've seen that elsewhere, but it's just the term that we use. Okay, let's get back that original sample again. Okay. So, well, let's look at the sample then relative to our contour plot for this probability distribution. And again, what this contour plot gives us is a two-dimensional viewing of the probability distribution, where each of the contours corresponds to, in a three-dimensional sense, what the height of this surface looks like from the multivariate normal distribution. So the higher the value, the more probability there is that indeed I would have a sample value from there. And so what we can see here for this, so I plotted these points, and how did I do that? So first of all, I did the contour plot just like what we did before, but to plot the actual points or the observations, I simply used the points function in R, where what's on my x-axis is going to be the x1 values, what's on my y-axis is going to be the x2 values. I make them red, and a line thickness of a point thickness of 2, twice the default, so they stand out a little bit better. And so this is what I got for the plot itself. And so, for example, if I come back up here, so let's find about the first observation was 16 and 20.4. So here's 16, here's about 20, and so that first observation is probably about might be right there. Okay, and we can see that as these as we get closer to the middle of these contours, these points tend to have, let's say, a higher density of points. It's a little bit harder to see since I only have a sample size of 20, but that's essentially what's happening here. So these observations make sense relative to the contour plot. Notice we don't have like a point out there. That wouldn't make sense because there's an extremely low probability of being that far out. Well, let's say that I had a sample size of 200 instead. We can take a look at the estimates there. And we can see that indeed these points are getting more dense as we get towards the middle of these contours. If I had a sample size of 2,000 instead, we can see that even more dramatically as well. Okay? So here's a question for you. So suppose I wanted to simulate a sample from a trivariate normal distribution, meaning that now I have a vector that has x1, x2, and x3 in it. What would I basically need to change in this set of code here? Just change mu, change sigma. So mu would have to have 3 means in it. Sigma would have to be a 3x3 matrix. So again, my code is a template for what you could do on your own. So why do you think it's useful to be able to simulate data in the first place? Any thoughts? Something I talk about always in Stat 801 because I talk about simulating data a lot.
To get an idea of the hypothesis you're trying to test. I mean,
That could be one reason. I think what you're kind of getting at is that you know what the population is. Okay, let's see what that sample would look like from that kind of a population. And so in other words, you know what should happen. Let's see if it actually does. And so especially then, when one is actually getting to more sophisticated statistical methods. What one would like to be able to do is test those statistical methods out on a situation where you have an idea of what's going to happen. You know, for example, we'll talk about this late in the semester. One could actually do a hypothesis test like this. So all of you have done hypothesis tests for one mean, but suppose you want to do a hypothesis test for a mean vector instead. Okay? So what we could do is simulate data from a multivariate normal distribution. Maybe it has 2 variables, 3 variables, 4 variables, however many. Calculate your test statistic, and every single time, check to see do you reject HO or not. Now, if you're simulating data, assuming that the null hypothesis is true, meaning that your multivariate normal distribution truly does have, let's say, some specified mean distribution, then, you know, if you're using alpha 0.05, you would hope to reject just 5% of the time. But let's say if it doesn't, then that can be a warning that, hey, this statistical method isn't working as advertised, you could say. And so this is used a lot in statistical research, but also in other research, to look at a situation where you know what should happen and you can test out statistical methods. This is especially important too because there are situations for some stuff that we will do in this class where we assume, well, let me say it this way, our more sophisticated statistical method that we have assumes that we do have a multivariate normal population. Well, you know, are you ever going to exactly have a multivariate normal population? Well, no. So will the statistical method work? And so what you can do is then do some simulation of data and see for some other kind of population, will the method still work or not? So then this gets into then the question of, well, how could you check to see if a sample actually, you know, is where it's reasonable to say that it comes from a population characterized by a multivariate normal distribution? Now, in your first stat course, or at least in a Stat 801 kind of course, if you were to, you know, you took a sample from a population, a univariate sample, and if you wanted to check to see, does that sample look like it comes from a population characterized by a normal distribution, you know, what would you do? Well, you would do like a little histogram, and you would look, does that histogram look kind of mound-shaped and symmetric? If it did, then you say, yeah, a normal distribution is kind of reasonable. And often what you also do is you will plot on top of it what looks like a normal distribution curve as well. And as long as the top of the histogram bars reasonably are approximated by this line that you drew, and I didn't necessarily draw it the best, but I think you kind of get the idea here. As long as it's reasonably approximated by the line, then you say, yeah, the normal distribution seems reasonable. Okay? Now, how could we do the same kind of verification then if we, let's say, had a bivariate situation? So we have 2 variables. We want to see, is my sample, like the sample that we just saw, is it characterized by a bivariate normal distribution? How would you check that? Any thoughts? Could you maybe do a like a 3-dimensional histogram? Yeah, why not? You know, where the bars, imagine bars coming up from like the bottom of the plot, bars coming up, and you would hope then that those bars kind of follow that same 3-dimensional surface that we saw before. Okay? Suppose though that you had a trivariate situation where you had 3 variables. How could you check to see if it's reasonable to say that the sample came from a population characterized by a trivariate normal distribution? And now it's going to be a little bit more difficult. How about 4 variables, 5 variables, 6 variables? Even more difficult. So we have some problems here. You know, if I say a particular statistical method relies on a multivariate normal distribution assumption, well, if I have 2 variables, I have a good way of doing it. 3 variables, 4 variables, now I don't have a good way of making a check. So what we can do is kind of go back to what we just saw up here. If I wanted to check for 2 variables, what I could do is do a scatter plot of the data. And it seems like all the points are kind of following the pattern of an ellipse. Then it might be reasonable for those 2 variables that indeed a multivariate normal distribution holds. But if you have 3 variables, 4 variables, 5 variables, I can't necessarily do a plot like this. So an ad hoc way to do something like this is to do basically all possible pairwise scatter plots of your variables, and check to see if the points kind of fall in an ellipse kind of shape. It's not perfect, but that's an approach that can be used. Okay, so let's go back to this this normal distribution again. Now we talked about a 3-dimensional histogram. Well, I'm going to get a little bit more fancier. I'm going to use what's called a kernel density estimator instead. So let me actually go back to one of our previous plots. So this is what that three-dimensional shape of our probability distribution actually look like. Okay. Now you might be wondering, well, is there a way that I could just simply do, fit a surface basically to the top of a histogram and just display that surface? And that's what's called basically a kernel density estimator. You know, what I want you to get out of this is the ability to apply it, not necessarily how it's actually constructed. Where would you learn about how it's constructed? You would learn about that in a non-parametrics statistics course, which would be like Stat 874. And so let's actually, it's easier to look at it for the 2000, the sample that has a sample size of 2,000. Let me actually just go back to it and run that code. Okay, I'll go through the code shortly. But this is what the surface looks like. And so again, you can imagine it as a three-dimensional histogram, and what we're going to do is just simply plot a surface that kind of goes right on top of the bars that are sticking from the bottom, sticking up from the bottom of the plot. And we can see from this surface that indeed it looks like it's very similar to that three-dimensional representation of the probability distribution that we had before. If I were to actually plot that probability distribution on top of it in green again, you can see how everything seems to nicely match up. I can even go down underneath of it to take a look at it too. And so again, we're getting what we would expect as well. And now if I had a sample size of 200, as you might expect, it's not going to be as well represented by that three-dimensional surface. If I had a sample size of 20, it's not going to be as well represented as well, but that's what it looks like. Now, how did I do this particular plot? Well, there happens to be a function R called KDE for kernel density, 2D for 2-dimension, and all I need to do to use this particular function is to put in the values of x, put in values of x1, put in the values of x2, save that into, let's say, f of x dot hat. So this is like an estimate of f of x. And then when I run the Perspect 3D function itself, for my x-axis, I simply grab out all the x values that are in my fx dot hat. So R has a way of looking at particular values of, all the x1 values. In other words, what's going to go on the x-axis. For what goes on the y-axis, these are my x2 values. What goes on my z-axis, those are my f of x hat values. And that's how I was able to actually put this on, to do this three-dimensional plot, to actually add my corresponding actual probability distribution itself. I do exactly the same code as what we had before, but now I have add equal true in there in addition. Okay. So the purpose of this little part of the notes was to say, well, yeah, it can be difficult to figure out multivariate normality, especially when you have more than two variables. Even when I do have two variables, we can see that, you know, like this little representation of the surface. And let's actually just run that. A sample size of 20 actually makes it still difficult to make a judgment. Oops, close that out. Makes it difficult to make a judgment of multivariate normality. I mean, look at this. I have two peaks to it. And so, you know, in the end, when you end up looking at all these scatter plots for, let's say, x1, x2, x1, x3, x1, x4, and so on, you know, just be careful in terms of don't be too picky. If you only have a sample size of 20, it's not going to be really enough to make a big judgment unless you have some really huge outliers or really big outliers. But once you start getting higher sample sizes, then you will be able to make a better judgment. Okay, let's move on here. Now, there will be multiple times during the semester where we want to work with what's called standardized data. And basically and you've probably seen this in like a Stat 801 kind of course before. But the basic idea of standardized data is that you convert the data to a unitless scale. So for example, with our cereal data, you know, we have sugar that's measured in grams. We have sodium that's measured in milligrams. But if I want to make comparisons between sugar and sodium, you know, they're in two different units. So perhaps what we can do is somehow transform those two variables to a unitless scale. And simply the way that we do that is as follows. For, let's say, your rth observation, experimental unit, for the jth variable, I'm going to subtract off the estimated mean for that jth variable, and then divide by the square root of the estimated variance for that corresponding variable. Okay, so why does this make this a unitless scale? Well, let's say that x sub rj is measured in, let's say, centimeters. Sigma hat sub jj could be, let's say, centimeters squared. Well, why do I have a square there? Remember, this is a variance, and when you find a variance, you end up squaring quantities. When I take the square root of that, of course, now I just have centimeters itself. And when I take xrj divided by the square root of that variance, now the centimeters cross out. And so that's why it's a unitless scale. You know, where did you see this before? Well, you know, when you often made this little transformation, like transformation when you were talking about a normal distribution in a Stat 801 course, that's essentially what you were doing. Now we're just doing it with sample values or estimates instead. Okay? And and of course, oops, erase this. My eraser doesn't work. Let's try this one more time. There we go. Now look what happens here when I do this little transformation. When I take xrj minus this estimated mean, suppose I just let that be, we'll just call it y for the lack of a better letter. What's going to be the mean of y now? So I take all the x's, subtract off its corresponding mean,
0?
0. Yeah. So we're centering it. We're centering it at 0. By dividing by the square root of the estimated variance, now what we're going to do is cause this whole thing called z to have a variance of 1. Just like what you learned about when you did this little transformation, when you were talking about, remember, the standard normal distribution. So z sub rj, I guess, sorry, I have the answers right here. If you have all your z sub rj, so r equal 1 to capital N, if you were to find the sample mean of all of them, it will be 0. If you were to find the sample variance, for, again, this is for the jth variable, if you find the sample variance, that variance will be 1. If you wanted to, you could put all these values into a matrix structure, such as what we have here, just organized in exactly the same way as what we've seen it as for an X matrix. So let's talk about this in the context then of the serial data itself. Just to verify that indeed that this is it's all true. So with the serial data, if you remember from last time, we were really interested in in columns 8 through 10 of the serial data set. This is the sugar, fat, and sodium values that have been adjusted for the serving size. Now, what I like to do is actually find the z's, the standardized values. And R, the function that does that, is called scale. Why does it use that word rather than, let's say, standardized? Well, you can think of this as all we're doing is just rescaling our data values. So that's why. And if I say scale, serial, columns 8 through 10, put that into Z, now I have my standardized values. So for sugar, just do this. So for this 0.4528, how did I find that? I took 0.45828, 0.4528. I subtracted off the mean of all the sugar values, which was 0.28. So I took 0.357. So for the first observation, 0.357, subtract off 0.28. Divide that by the standard deviation of all the sugar values, 0.15. That's how that 0.45 came about right here. You can verify that on your own. Let's take a look at then the estimated covariance matrix. So for the Z's, the Z version, the estimated covariance for sugar and fat is about 0.24. The estimated variance for sugar is 1. Remember, we said that we would expect that. The estimated variance for fat, the Z's, is 1 as well. Let's take a look at the correlation matrix. Wow, look at that. The covariance matrix is exactly the same as the correlation matrix. That's kind of interesting. Well, why does that happen? Well, let's take a look at this. Covariance of, let's say, Z1 and Z2. So I have two variables, call them Z1 and Z2. Actually, I'm sorry, let's do correlation. Okay, correlation of Z1 and Z2. Well, that would be the covariance of Z1 and Z2 divided by the square root of the variance of Z1 times the variance of Z2. So these are population quantities, but you can do the same thing with the sample quantities as well. Remember what these variances are? 1. So In terms of population quantity, the correlation is for Z1 and Z2 is equal to the covariance for Z1 and Z2. Same thing happens with the sample, and that's what I just demonstrated with the serial data. So that's why this happens. How about we find then all the means of the Z's? And notice for sugar, fat, and sodium, they're all 0, essentially. The only reason why they're not exactly 0 is because of wrap-off there. Okay. Now, there's something else that's interesting to take a look at here, too. Let me come back over here. So let's take a look at the estimated correlation matrix for the x's. Look at that. It's exactly the same as the correlation matrix for the C's, as it is for the, and that's exactly the same as the covariance matrix for the Z's as well. So that's interesting to see that. Any thoughts about why that happens?
Because the variance is 1. If the correlation equals the covariance, if the product is 1, right?
So I mean, the variances of the Z's is equal to 1.
Right.
Okay. So, but note that we have, so basically we're saying this. Okay. And well, why does that occur? Excuse me. It has something to do with the variances, yes. But I want you to all think about that some more outside of our class. And if you're unsure what the reason is, let me know. We can talk about it during our next class. Okay, let's move on. So the last thing that we're going to do in this section of the notes is that we're going to talk about how eigenvalues, eigenvectors, and talk about their role relative to the multivariate normal distribution. It's kind of interesting. So we're going to be looking at the covariance matrix, sigma. And we could find, notice that, of course, that's a square matrix. So we could find eigenvalues, we could find eigenvectors. So we're going to let lambda 1 be the largest eigenvalue from sigma. Lambda 2 be the second largest eigenvalue from sigma, and so on. With each of these eigenvalues, we can find eigenvectors. So the first eigenvector would correspond to lambda 1. The second eigenvector would correspond to lambda 2, and so on. Now, the first eigenvector, remember, we can actually plot those. And it will, and let's say that we have a bivariate normal distribution situation here. The first eigenvector will point in the direction of what's called the major axis of the ellipse. In other words, where the ellipse is most elongated or stretched out. The first eigenvector will actually point towards that, you can say that axis or that direction. The second eigenvector will point in the other direction. You can say what's called the minor axis of the ellipse. So to help demonstrate that, let's go back to this bivariate normal distribution again. And I did a plot of the ellipse. Now, one thing that I did, I did a contour plot for the normal distribution. One thing that I did differently from before is I just changed the x-axis and the y-axis limits so that I had a little bit more room to plot the corresponding eigenvectors. Also, I only plotted 2 contours because we didn't need to see them all. So just to plot 2 contours, all you need to do is, where's the argument? There we go. There's a levels argument in contour that allows you to specify which contours you want. And I said I only wanted 2 of them. Here's my eigenvalues and eigenvectors. Notice that there's a small little change to the code there. I actually I should have put sigma there rather than for some reason put code.mat. So I can put that in eigen, and then of course I can get the eigenvalues out with the values argument or values component of the object that I saved. I can also pull out the vectors as well. I can plot the vectors with the arrows function as we did before. And so what we can see here is that if I were to draw what are actually the major and minor axes of ellipse, you would probably, I don't know, I think I first learned about ellipses when I took my 2nd year of algebra in high school. And major and minor was defined there. If you don't remember it, that's fine. Just again, think of major as where the largest spread out portion is, minor is where the smallest spread out portion is. And we can, and this here corresponds to the first eigenvector. Let me just actually go back up here. So that is 0.62 to 0.79. This one right here. And we can see that indeed it is pointing in that direction of that the major axis of the ellipse. Here's the second eigenvector, and it's also pointing in the direction that I just had stated before. And so that's kind of interesting, the relationship then of eigenvalues and eigenvectors with the multivariate normal. But there's more to this. Okay, let me make sure I get this right. Okay, to see the more. To see the more part, let's make a small change here. Let's let the variance of x do 2. Instead of being 1.25, I'm going to make it 0.26. Now, I didn't want to go any lower. And the reason being, and when I was going through my notes yesterday, I was thinking, maybe I didn't emphasize this before. Let's actually, where's that multivariate normal? So in the definition of the multivariate normal, yeah, I guess I did say that. Notice how we have the determinant of sigma there. And the determinant of sigma has to be greater than 0 for this multivariate normal distribution to exist. And this is equivalent from a univariate normal situation where you say the variance is greater than 1. I'm sorry, variance is greater than 0. Okay, it doesn't make sense to have a negative variance. If you have a 0 variance, well, then that's no fun. All your data values are just simply 1 point. Okay? And so we need to make sure that the determinant of sigma is greater than 0. And so when I chose the variance of x2, when I made the change here, I chose it to be about as low as I could get so that the determinant was still greater than 0. Okay? Now, if you were to go through the same calculations with the eigenfunction, you would find that lambda 1 is 1.25 and lambda 2 happens to be 0.01. This leads to also, in this kind of a covariance matrix, a correlation of 0.98. So extremely strong dependence between x1 and x2. So think about what that means. That means that if you know what x2 is, you have a really, really good idea what x1 is. Okay? Here's what the contour plot now looks like. Notice how everything's been kind of compressed in the minor axis direction. We have these narrow bands there for the ellipses, for that contour. And so, if I were to take a sample, as what we've seen before, I would expect my sample values to fall, right around there only. Now, you could plot then the corresponding eigenvectors, and that's what I did there. Now, is this alarming at all that notice that this has changed directions? This is for the major, this is for the first eigenvector. Is that alarming at all? It shouldn't be. Because remember, you can simply rescale eigenvectors, and that was actually part of a problem on the last quiz. If I multiply it by -1, it just flips things. That's all. But it's still pointing in the same direction of, I'm sorry, this is for the second. The second eigenvector, this is for the first. So there's nothing to worry about in terms of, the directions are flipped, but it's still pointing in the correct direction, I should say. And, you could keep on, if you wanted to, you could keep on making this a little bit smaller, this variance here. That's going to cause this eigenvalue to be even smaller as well. And eventually, as lambda 2 goes to 0, the contours essentially will become a straight line. Now here's why this is all important to us as we go along this semester. So, probably back in elementary school was when you first learned about how you could plot stuff in an XY coordinate system. And depending upon what you've learned in other courses, you might not know this, that, here's my x-axis, here's my y-axis. How about I just simply rotate those axes instead? Suppose I rotate them in a way, let me actually get a different color pen out. I could rotate them in a way that they follow the same directions. So this is my new, the new y-axis. I could rotate them in a way that they're still perpendicular to one another or orthogonal to one another. And I could look at this, keep the ellipses in the same spot, the contours in the same spot. But I could rotate my axes and come up with a new, you could say, coordinate system like this. So I could have a new x-axis value and a new y-axis value corresponding to these ellipses, corresponding to if I were to take a sample. I could do that. And in fact, we will essentially do that as we go along in the semester. Now, ignore the old x-axis and y-axis. We can see with the new x-axis, we have some variability. Based upon where those contours are. And again, think about where you would expect the sample to be. We have some variability in that direction. But we have very, very, very little variability in the new y-axis direction. So if I wanted to understand, let's say, a population that's characterized by this particular bivariate normal distribution, would I really need to know what the value is for this new y-axis relative to my, let's say, my data values? No, because there's going to be very little variability. All the information about my population is basically centered about these new x-axis values now. Because I can see where the variability is, I can see where the mean is. But there's very little information being contributed by this new y-axis. And look at, again, this characteristic here. This happened when one of those eigenvalues was very close to 0. What we will learn about coming up is that the variance in this new y-axis direction is equal to this, that second eigenvalue. We'll learn about that when we do principal component analysis. So let's extend this to another situation. Suppose instead of having just 2 variables, suppose I had 10 variables. And I have a multivariate normal distribution like this. And understanding data that has 10 variables in it, as you can imagine, can be kind of difficult. You have 10 things to worry about now. And if I had the covariance matrix with it, and let's say that only one of the eigenvalues was basically non-zero, then that would tell me is that there's a way that I can look at my data in a different way. You know, think about rotating in 10 dimensions if you can think about that. I can rotate my data in a way where now I only need to worry about one, let's say, new variable out there that's based upon those other 10. And that will give me all the information I need to know about my data. You know, very rarely will that happen where you have, let's say, all your eigenvalues be essentially 0 except for 1. But, you know, let's say, again, if I have 10 variables, and let's say 3 of the eigenvalues are essentially non-zero, and the other ones are about 0. Now I can look at my data in a 3-dimensional sense with 3 new variables and get the same information out of it as if I would have looked at it with 10 dimensions to begin with, 10 variables. And so that is the motivation then behind a number of multivariate data analysis methods. That same concept. Now this is the last thing that, suppose we have, in this part of the notes, suppose we had a trivariate normal distribution. So now you can imagine, let's say, an x-axis, a y-axis, and a z-axis. And one could actually plot contours in a 3-dimensional sense for that trivariate normal distribution. And in fact, the contours would look something like this, a football. So imagine this football is in space. We have an x-axis, we have a y-axis, we have a z-axis, okay? And this could be, let's say, the f of x is equal to 0.01 contour represented by the surface of this football. We could then look at, let's say, a different contour, and we get a little bit of a smaller football. With this contour, do you think would that be a larger value for f of x or a smaller value? Sorry, it would be larger. But thank you for volunteering. Because again, we're getting towards more the center. And the more we get closer to the center, the larger the contour will be because we have more probability associated with observing values closer to the center. And, perhaps I'm going too extreme here as I get all my kids' sports equipment. Here's even a smaller contour. Okay? Now, so we're going to have 3 eigenvalues corresponding to this. Again, extend that 2-dimensional case to now 3-dimensional. We're going to have 3 eigenvalues. Are any of the eigenvalues going to be equal to one another, do you think? Or will they be different? These eigenvalues correspond to, as what we saw, well, perhaps I didn't say this very well. Yes, I did mention this briefly. This lambda 2, in the 2-dimensional sense, actually corresponds to the variance of this new axis. Lambda 1 corresponds to the variance of this other new axis as well. Okay? So now I have 3 eigenvalues here. And I'll just give the answer because I didn't explain it very well there. 2 of the eigenvalues will be actually the same. The reason being is because if you can think of, let's say, an eigenvector going up like this, and also an eigenvalue going up like this, going out like this, think of new axes. Essentially the football here has the same, how should I say, the same in I guess this direction and also this direction. If you look at the center of it, it's always going to be the same in terms of the distance. Now what we can see here is that the football is more elongated to one distance, so my lambda 1, my largest eigenvalue, will correspond to this. Its corresponding eigenvector will go that way as well. Now let's say that you are a quarterback for a football team. How should I put this? Well, I'm sorry. Let's say that you're Tom Brady. Now, a few years ago, Tom Brady became connected to something that was kind of cheating in football. where he wanted the size of the football to be changed in a certain way. Does anyone remember what was called Deflategate? Okay. So anyway, for a playoff game, I don't know, this might have been 10 years ago. For a football game, supposedly, well, I mean, I think it was kind of proven it was, that his team was New England Patriots, some member of the New England Patriots staff took some air out of the football. And the reason being is because if there's less air in the football, with your hand you can grip it better. You can probably throw it better as well then. And supposedly Tom Brady, people think that he got somebody to take the air out of it so that he could throw the football better. Now think about if I were to take all the air out of this football, so now it just becomes a two-dimensional object, essentially, if I could completely flatten it out. Now think about what that will mean in terms of the eigenvalues. Lambda 3 will now be 0 because I have no variability in one of the directions now. Okay? Oh, I have more props. Since in my notes I talk about it in basketball, but I think we're more of a volleyball school now anyway. And we had 8,600 people at the Devaney Center last night. That was amazing how they fit everyone in there. I would imagine that at least 500, 600 standing room only people were in that arena last night. And so we have a volleyball, and a volleyball is pretty much symmetric. Okay? What do you think about now the eigenvalues? All the eigenvalues will be exactly the same. Okay? So this could be one contour. A larger contour would be, let's say, this here as well. And again, if I were to smash this down so it's essentially two dimensions, then one of the lambdas will become 0. And if I could really, really smash this down so it's basically it was a single small point, if I could somehow do that, all the lambdas essentially would be 0. Okay? So towards the end of the notes, you're going to see the same description. This is just where I've seen this kind of same description before, and I thought it was the best place. This is out of Dallas Johnson's textbook, where he talks about footballs and basketballs. And the very last thing in the notes was something I've already discussed as well. Okay, so are there any questions? Let's see here. Hold on a second. I thought I had my next set of notes open, but for some reason it must have closed. Okay. Okay, so that concludes section 1 of the course. I would say a lot, and I'm kind of repeating myself, sorry, but I say a lot of those topics were kind of light. I'm sure, you know, maybe the eigenvalues, eigenvectors, and multivariate normal wasn't, but light in terms of content. And I think we have maybe one more set of notes that's kind of like that, but it's still very important. This is this is the graphic section. And so this part of the course, let me actually go to this right here. So we had section 1's background material. Section 2 is summarizing data. So remember I talked about principal component analysis briefly earlier, and there you can see where it is. And so the purpose of the summarizing data is that, you know, we have this multivariate data. People often refer to as multidimensional data because I have multiple variables. And I want to be able to summarize it in some way to make sense of it. And one way to do this is through a plot. You know, if you've heard of the phrase, a picture is like 1,000 words, or some phrase like that. And I believe that in terms of, let's say, statistical graphics. If you can really graph something that can really make sense of a complicated situation. So we're going to look at ways in that we can try to get as many variables as possible being displayed on one plot. Okay, and why do we do this? Well, we want to, let's say, look for trends in the data. We want to look at, are there any unusual observations or observed values for experimental units out there? And also suggest items to examine in, let's say, a more sophisticated statistical analysis. Suppose you are going to do some kind of sophisticated statistical model. You might get ideas of particular models to look at, given, let's say, an initial look at your data. But once you do that sophisticated statistical analysis, you can use then these kinds of plots or these techniques that we're going to see here to make sense of it. And so you're going to see me throughout the semester, once we get to more sophisticated statistical methods, like, let's say, principal component analysis, we'll always look at plots to try to explain what's going on. Okay. Now, there's going to be a lot of code again. I think this is, and we'll always have lots of R code in our course, but I think this is like the peak in terms of the amount of R code that there is. Again, think of my code as a template for your own. I will primarily use the serial data in this set of notes to illustrate stuff. Now, and the reason why I do that, I try to be consistent with the exact same data set. It's just so that you can see the data being examined in multiple different ways. Some plots I probably wouldn't do with the serial data, but it's a good place to start. And also with the serial data, we have 3 primary variables that we're looking at and only a sample size of 40. So it makes things easier in a teaching context. We will also primarily be using functions from the graphics package in R. This is automatically installed in R. You've already used it for our class when we've seen like scatter plots and also like the contour plot. With this particular package, because it's always R, without getting all the details, R always makes that package ready to go for you, so you never have to actually ever say library graphics before you use functions from it. Now, there are other packages out there that do graphics. We've seen, for example, the RGL package, for example. Graphics package is the one that's most used. There's another package that has become widely used, and it's called the ggplot2 package. I primarily do not use ggplot2 because in order to get, let's say, publication quality plots, which is part of my job, I need to publish or perish. In order to get publication quality plots, and also just plots in general, often you need a lot more code to do this stuff than you would with the graphics package. There's a lot more functions that you need to learn in order to use the ggplot2 package than you would with the graphics package. So that's another reason why I don't like to teach with it. So if you've by chance come across ggplot2 before, that's why I don't use it. Okay, so we need to start somewhere in the graphics section. And we need to start with a scatter plot. We know how to do that, and we can use simply the plot function to do that. But let's say that we have more than 2 variables. So what we could do is, let's say, do scatter plots for each pairwise combination of variables that you could look at. You may or may not have seen these before. And when you do all pairwise possible combinations of these plots, it's called a side-by-side scatter plot or a scatter plot matrix. So if I go into the serial data itself, there's a function in the graphics package called pairs. So all pairwise combinations. So I say pairs, and then the first argument is formula. And the syntax is a little bit weird, or maybe a little bit weird to you depending upon your background. And we say equal, and then we say tilde, sugar plus fat plus sodium. So the plus basically means and. I want to plot sugar and fat and sodium. My data is in serial itself. And so if I go ahead and run that segment of code, I get this plot right here. And so what we see is basically a 3x3 matrix of plots. On the diagonal, you simply have labels. So in the 1, 1, you could say part of the plot, row 1, column 1, I have sugar. 2, 2, I have fat. And if I match up, let me just come on back over here to Word. So if I match up sugar, if I match up fat, you can see here is now the sugar and fat scatter plot. Here are the values for fat. Here are the values for sugar listed there. Do we see any kind of trend there? Not really much at all. Okay? That shouldn't be surprising. If we look at our correlation matrix, look at the estimated correlation between sugar and fat. It's positive, but it's kind of low. And in fact, if you look at all the other correlations, they're all kind of low in terms of relative to 0. And so if you look at, let's say now, sugar and sodium, we don't see much trend. If we look at fat and sodium, we don't see much trend as well. Now, in this set of notes, when there is maybe another function out there that provides somewhat of a better plot than what can be done in the graphics section, I'm more than happy to actually illustrate that to you. And so, for example, in the car package itself, there's a function called scatter plot matrix. It has the same syntax in terms of the formula and data argument, and this is what we get. And so we can see that we have a lot more information being displayed. Now, on the diagonal of this plot, we again see sugar, fat, and sodium. But notice we have some curves on it. Does anyone know what those curves are representing? It basically estimates the distribution. In fact, it's a kernel density estimate of the corresponding distribution. And this helps explain what a kernel density estimate is in a one-dimensional sense. And basically, if I were to do a histogram, there's my histogram. That's what it would look like. So it's just giving me the top of that histogram. And so one could say, let's say that you've heard of the term modal in statistics, where a mode is the highest point, or I'm sorry, the most frequent point, let's say, in your sample, in terms of a probability distribution itself. It could be parts of the distribution where you have significantly higher probability. And in this context, notice I have 2 peaks there, so we can say that it's bimodal. Down below here, we have what's called a rug. And what the rug basically is giving little marks to show where the actual data values fall. So for example, between about 0.3 and about 0.5, I see I have a considerable amount of values for sugar. Now if we look at sugar and fat together, we see a simple linear regression model, that's a straight line. It's trying to give you an estimate of the association between sugar and fat. Notice that that line is fairly flat, horizontal. Remember what the correlation was? About 0.24. And so that's not surprising. It says, again, that there's not much of a relationship between fat and sugar. So as fat changes, we can't really say much about what's happening with sugar. The dashed line there is what's called a smoother. Again, where would you learn about that? In like a Stat 874 class, a non-parametrics course. You might also learn about it in a Stat 870 course for regression analysis. What you need to get out of it is basically what the smoother does. It tries to approximate the trend in a nonlinear manner. So it's not confined to just a straight line. And so, we can see a little bit, well, maybe there's some kind of association that's happening there. You can see this, extending out from the smoother. We see, there's a specific name for it, I can't remember, but in terms of, we see some stuff colored, but what's actually being colored out to is basically what amounts to a 95% confidence interval for specific values of fat. What would be the 95% confidence interval for what the mean value for sugar would be. And so that's what we see coming out from that. And overall, maybe for the sugar and the sodium plot, which is this one, and maybe we have some kind of quadratic trend that's going on there. So something that we maybe didn't really notice before. It's definitely not really a big trend, but maybe there's something there that maybe we could explore later on. Okay, so we are out of time here. Let's just review what's next in our class. Again, I'll have my office hours. Monday, do not forget, we have a week number 4 quiz that's due at 5 p.m. Again, the reason why I make it due Monday versus Wednesday is so that if there's some issues that I see with the quiz where students are missing, many students are missing particular problems, this will allow me then on Tuesday to address that before our test that is on Thursday. So on Tuesday, we will continue in this graphics section. We will also do a test number 1 review. We have our tests on Thursday. I don't know why I put that as looking further ahead. It's right there. So any questions? Okay, that's all for today.